Okay, so let's look at this last example here. What we have been doing this entire time is finding the area of the region bounded by the x-axis in the shape, which would be that area that I'm pointing to now. But we don't technically have to do that. We could also find the area of the region bounded by the y-axis in the shape. So what does that do? Instead of having vertical rectangles, we now have horizontal rectangles. So theoretically, we could do a problem like this as well. I do want you to see this because when we move on to Calc 2, you are going to have to find the area, the sum of horizontal rectangles. So I at least want you to see this concept, but I am telling you that it will not be on the test. Okay, so I'm not going to put this on the test, but this concept is really, really important because you are going to see this concept in Calc 2. So what are we going to do for this one? Again, what we need to do is think about the area. To find the area, that's going to always be the height times the width. But here, instead of our width being fixed, our height of every single rectangle is going to be fixed. So again, let's think about this process. The first thing is the number of rectangles. Well, we still want in rectangles. Sorry, I haven't formally read the problem, so let me do that. It says, find the area of the region bounded by the graph of f of y equals y squared. So it's a function of y now, right? The y-axis, and 0 is less than or equal to y is less than or equal to 1. So number 2, let's think about the width of every single rectangle. Well, the width now is not the change in x. The width is now the change in y. And that's going to be the top y value, which is 1, minus the lowest, which is 0, divided by the number of rectangles. So now this is 1 over n. So the width of every single rectangle is 1 over n in this case. Number 3, let's think about drawing that interval. But now my interval has to be horizontal. So this is really going to kind of mess with us. Remember, we're not finding the height of each rectangle now. We're actually finding the width of each rectangle now. So it seems really weird to me, but this is what it is, right? And we have to find it for the general rectangle here. So again, how do we find the distance over here that we're going to use for a general rectangle? Is we actually have to find out what the function value is in terms of y, right? So here's our rectangles, and we're using our general rectangles. So it starts off with 0 and it ends with 1, and then we add the height every single time, and we decided the height is 1 over n every single time. So our change in y is 1 over n. So this would be 1 over n. The next one would be 1 over plus 1 over n, which would be 2 over n, and then we'd have 3 over n. So it seems like on the first rectangle to determine the height, below it's 0, above it's 1 over n. On the second one, below it's 1 over n, above it's 2 over n. So it seems like for the ith one, it's 1 less over n and then the same number over n. So the ith one would be I minus 1 over n, and then I over n, right? So that would be the general one. And again, I can choose either of those numbers. The easier of those numbers would be I over n. So what function value am I plugging in for y? I'm going to plug in the ith over n function value for y. So the height of it, again, this is going to be f of y sub I, and the width of it is going to be the change in y. We just have to think about this in a different direction. And for the total area, we need to sum that from I equals 1 to n, all of our rectangles. So what do we have here? We have the sum of I equals 1 to n of, well, f of y sub I, that general, or c sub I is what they use. The general one we decided is I over n, so this would be f of I over n. And then the delta y, we decided the change in y every single time is 1 over n. So this is the same thing as the sum as I equals 1 to n of f of I over n. Well, my function is y squared, so this would be I over n squared, and that's times 1 over n. Again, this would be the same thing as the sum as I equals 1 to n of I squared over, well, it'd be n squared times n, which is n cubed. This is very similar to the previous problem we saw, right? So this is the same thing as, well, 1 over n cubed is a constant here, and this would be the sum of I equals 1 to n of I squared. But that's a formula that we know. The formula that we know for I squared is, that turns into n times m plus 1 times 2m plus 1 all over 6. That's from a formula on the first or second page of the notes. So if we have n rectangles, the sum of all n of them would be 1 over n cubed times n plus 1 times 2n plus 1 all over 6. I'm going to do some simplifying. This would be n squared, and that would be a 1. I'm going to go ahead and FOIL out the top. When I do that, I'd have 2n squared. Sorry, let me use black. I'd have 2n squared, then I'd have plus n plus 2n, which would be plus 3n, and then it would be plus 1, and all of this would be over 6n squared. So if we found the area within rectangles, horizontal rectangles, there would be 2n squared plus 3n plus 1 all over 6n squared. Okay, that's using the upper endpoint instead of the lower endpoint for each one of those. But again, that's for n rectangles, and what we wanted was as n goes to infinity. So let's look at the limit as n goes to infinity of 2n squared plus 3n plus 1 all over 6n squared. And when you do that, this is a balanced. And when it's balanced, it goes to, just look at the leading terms is all you have to do. So that would go to 2 over 6, which would be 1/3. So what's the area beneath the curve of, or not really beneath the curve, technically it's above the curve, right? To the left of the curve between the y-axis and the graph of y equals x squared here, which is the same thing as the square root of x, by the way. The area beneath or between those curves would be 1/3. So it's just a little messed up on this one. Again, the y ones, it is possible to do. You just have to realize that you're not dealing with delta x, you're now dealing with delta y. And then you have to realize that you're not dealing with a function of x, you're dealing with a function of y.